I'm working at Volvo Cars as a team leader for a shared service for the whole company, and we are specializing in graph technologies. And also as a product owner for what is becoming Volvo Cars' graph intelligence platform. And I will tell you today how to build a car then with the help of graphs. So let me start by telling you about the challenges of complex product development. So let's see. Is a Volvo a complex product? So what is a Volvo? A Volvo is about 100 communication buses transmitting information all around the vehicle to 200 control units, computers if you like, that are supporting you while driving your Volvo. Those 200 control units are delivering about 400 functionalities, like braking, accelerating, all the way to pedestrian collision mitigation, for instance, through massage, audio, GPS, and much more. Those 400 different functionalities are realized by about 2,000 software components, so pieces of software, applications, if you want. Processing, exchanging, and making sense of about 10,000 signals coming from all parts of the vehicles. Not to forget that cars are still a bit of hardware too, so they are made of about 30,000 mechanical parts, from screws all the way to windshields. And all this has to work together is in any of the 1 million possible configuration of a single vehicle that you can choose from when you go on volvocars.com website and design your favorite car. And yes, you're also right to expect no critical bug or safety issue when you're driving your Volvo. So how do we keep track of all that information? Well, I think we do like most of you guys here. We make tables in Excel, drawings in Visio, models in Rhapsody, even reports in PowerPoint. We store data in relational databases, often through the use of specialized tools that enable collaboration, version management, like Team Center and System Weaver, for instance. And the problem here is that all that huge amount of information and all those different sources of data actually describe a single product and how to build it. And they are handled today as silos, principally. So it's very difficult to navigate and to get the big picture, to comprehend how everything relates to the rest of the data we are working with. So a solution could be, as I've heard it said quite often, to reduce the complexity in our products. But that won't be easily done, because this is what you will see here is what on Volvo Cars near horizon. So we have autonomy coming. So Volvo's driving themselves. It doesn't sound like something that will make the product more simple, less complex. It will be less complex to drive, maybe, for the end user, but more complex to build. Electrification. Every new Volvo launched from 2019, so this year on, will have some level of electrification, which is new for us as well. So we need to cope with that. Connectivity. Volvos already are and always will be more connected devices. So already today you can use your mobile phone to lock or unlock your door. You can find your car if you've lost it on the map after a good evening with your friends. You can check the status, see if you need to go and refill, go to the gas station before going to work, for instance. But in the future, much more will be possible, like, for instance, downloading new functionalities that you didn't think was interesting to buy when you got your car. So you can change your mind. Sharing. Volvo Cars is working now on a new advanced car sharing solution, so that in the future, a very near future, you don't really need to own a car if you don't want to. You can also just always get the car you need at the time you need without owning it. And above that, We have to deal with multiple brands, multiple segments, because we are not alone in the GD group, and it's a chance to be actually able to share platforms and solutions with, for instance, Link & Co. or Polestar, but it's also bringing new challenges. What do we have more? System of systems. Yes, our cars will be part of smart cities. They will communicate with their environment, other Volvos, other cars, maybe not Volvos, and also infrastructure. Crowdsource data. By sharing data through the cloud, the cars will be able to support the drivers in making the right decision better than before. Machine learning. Yes, machine learning. To predict maintenance needs, for instance, or increase the driver or passenger convenience in the car. Third-party access, like in-car delivery, in-car pickup, digital concierge service, fueling, servicing your car at night while you're sleeping, for instance. Personalization, so that whatever Volvo you use, it always comes with your favorite setup, your favorite settings and application. So you feel yourself home each time or you feel yourself in your car each time you get a new Volvo or borrow a Volvo. Product evolution, so that your car gets better every day. Getting new upgrades for the functionalities in your car. We want to also reduce the time to market, because we want to deliver a new product to our customers at a faster pace. And all the unknown. So claiming that we can make our product less complex is an illusion. A car today is probably one of the most complex consumer product available on the market today, if not the most. However, it's very interesting to be able to understand the complexity in our product. Understanding the complexity in our product can be a very good idea, because we want to understand the part of the complexity which is accidental, the part that shouldn't be there, that is there because we use the wrong tools or the wrong methods. So we want to understand that part of the complexity. And we also want to understand the essential part of the complexity in our product, so that we can manage it. The essential part of the complexity is the absolute minimal level of complexity that needs to be there, so that we can deliver all our promises, together with quality, safety, and convenience. So how do we do that when we need to deal with always more data, and this data is organized in always more silos? So we need to understand the big picture, right? We need to be able to navigate the data. We need to be able to understand how everything is integrated with the rest. We need to understand our system's complexity and make sense of it. So let's see how graphs can help us with that. So what can we do with graphs in order to get support in building Volvos? We can use them to interface our many data systems, revealing existing dependencies that are today hidden in dark repositories. That's one way to use them. We can then use this information to mine knowledge out of that was hidden before. And we can mine knowledge with the help of graphs from different focus angles. We can look at the big picture, go a little bit more deep into the graph at subsystem level, let's say, or go all the way down to the detail. And the detail, what it is, it can be anything. We can even use them together with great data visualization tools as modeling platform. So we can actually model the data directly in the graph if we want. And obviously, we can run graph-enabled analytics. Like, for instance, Dsm Analytics, Design Structure Matrix Analytics, which is illustrated here, which helps us find loops in our system design, and you will see why it's not so good in a demo after that. Find clusters, sequences, helping us make some nice project planning. And all this can help us understand the quality of a system design, and even help us find improvements for it then. Also, we can apply artificial intelligence solutions, such as machine learning or natural language processing, for instance, to enhance the knowledge graphs. by predicting new relations, for instance, or bringing more semantic, more meaning into the graph. We can also feed graphs to the machine learning engines to improve their prediction potential. So it's a nice two-way relationship between artificial intelligence and knowledge graphs here. So it's quite a lot of interesting application that can support us in our product development operation. And so what do we do actually at Volvo Cars with graphs then? We do all that, in fact. My team is developing an application of our Neo4j database, which one use case at a time connects existing data systems in use at Volvo Cars today, that you can see on the left, for instance. It's just an example of those. And we also deliver a user interface, graphical user interface, for people to be able to understand the data, manipulate it, analyze it, etc. A byproduct of integrating use case by use case those new data sources into the application, into this tool, is the construction of Volvo Cars' own knowledge graph. And the potential, what we will be able to do with this knowledge graph today, is very difficult to grasp still. We are just discovering the potential of it. And to make this even better, we have an AI layer on the front to enhance the data in the knowledge graph. So we'll have a look at a little demo now. System engineering, what we are doing with graph for system engineering. So the demo will be focused mostly on one of those use case that comes into this application that we are developing at Volvo Cars, and it's called functional disposition. So Volvo Cars functional disposition, the goal of it is to build a functional map of all our product functionalities based upon our customer needs. So we started looking at our product from a customer perspective and from all possible usage contexts. So starting from that, we could map the product functions on the bottom layer in a way that describe how they together realize the customer needs in the different usage context. So in this example, for instance, a customer need is climate comfort. And climate comfort in the car can be achieved in different contexts. When you're sitting in your car, or maybe when you're having your breakfast before going to work. So depending on the usage context, the solution to deliver at the product level, the solution to deliver this customer need, climate comfort, might be different. So here is a very simple example where we see that two product functions, one of them is called temperature management and the other one airflow management, together deliver climate comfort. Temperature management needs airflow management to affect airflow. So this is how it looks today, and I think it doesn't render very good on the big screen, unfortunately. So I tried another just before. I tried to put that on a white background. It looks a little bit better, but it's not a huge graph. It contains a few tens of thousands of relations, maybe, only, a few thousands of nodes. But what's remarkable with this graph is that none of the information making this graph was mapped in any data systems before. The only thing we had was a list of functionalities. So all this information, which is mapped in this small graph, but tens of thousands of relations anyway, was basically in the brain of many Volvo Cars employees who together had this knowledge. So we mapped the common brain of function owners at Volvo Cars in a graph. It took a few years to build. We started 2015, and it's not even complete yet. We are like maybe covering 80%, 85% of all the use cases. But this has already become one of Volvo Cars' most valuable knowledge source. Because we build a lot over those functionalities and how they are integrated with each other, nearly the whole car. So let's see what we can do with that. in a little demo. First, we'll have a look at what we can do with functional disposition graph from a function owner perspective. So a function owner is someone who has the responsibility to specify and develop a functionality. Then we'll have a look at how functional disposition can be used from a system design analyst perspective, and then from a project leader perspective. So we start with the function owner perspective. So I'm going into this application, this Volvo Cars graph intelligence platform, and I will go into the user interface to functional disposition. So the graph is stored in a Neo4j database. And I want to have a look at this functionality, global opening and closing, because I'm responsible for it. So global opening and closing is basically a user need. It's when you click long enough on your lock button on your key. If you've left your windows open and your sunroof open, it should lock the car and close the windows and close the sunroof. And the opposite happens when you unlock your car. So here we can, yeah, it looks okay. It's readable. So it's a simple example. It's only 4 product functions involved in the realization of this customer function, this customer need, global opening and closing. One of them actually has the same name as the customer need. That's not an issue. And we see how they interact with each other. So we see that global opening and closing needs basic central locking to know when to lock and unlock the vehicle. And we also see that sunroof maneuvering and window maneuvering needs global opening and closing to know when to start closing or when to start opening. So when we have that information, we know that changing something on one functionality might have an effect on those. So maybe I should work with the people responsible for this other functionality so that we make sure that they still integrate very well. Before, it was all in the head, as I said, of many people. So they had to make sure they invited the right person to the project meeting and workshops, etc. So what we can do also, now I will go directly to Neo4j, in fact. I hope it will look good as well with this strange resolution. So that's basically what I've shown you. We have 4 product functions, and we see how they interact with each other to realize global opening and closing. When I have that, I can also ask, who should I collaborate with? Here is the list of the people involved in the realization of this product function. I'm sure I will invite the right person to the workshop. Then maybe I want to know what other customer functions does my product function contribute to? Because it might well contribute to more than that. So now let's say I'm the function owner for another function which is called basic central locking. I just asked Neo4j, and I know that it's involved in global opening and closing. We talked about it just now. But also in welcome light. When someone unlocks the vehicle, there will be something happening with the lights. So it makes sense. I might want to know also, does my function relate to another customer function I can think of now, like hazard warning? Hazard warning, you know, it's you have to brake very hard. There is an obstacle in front of you on the highway. Your blinkers will blink to warn people behind you that something has happened, so that they get some signal. So let's see if there is a relation, and yes, there is a relation, because I choose the use case properly for the demo. Basically, we see that basic central locking needs hazard warning illumination to illuminate lock and unlock. And yes, probably you've noticed on your car that when you lock your doors, then there is a little blink happening to let you know that something has happened. The car is locked. So this is something that is mapped also in functional disposition. So you get an overview. You can navigate your environment. You can make sure you always have the right understanding of how your product function integrates with the rest. I do a change in the specification, I have to talk with those people, because probably I will affect their work. Okay, so let's have a look at another use case. Yeah, so from the system design analyst perspective, so what can we do here? We can do Dsm Analytics. DSM stands for Design Structure Matrix, and it's basically the adjacency matrix in your graph. You might know what it is since you all are graph people, but it's basically the representation in a matrix of your graph, of all relations between the different components in your graph. It looks like in this example. With Dsm Analytics, system engineers can get information about the quality of their system design, and project leader can get help to organize and plan their project. So how so? What can we do with Dsm Analytics? Well, we can find out if there are feedbacks in our system. So Dsm Analytics works in the matrix plane. Most of the tools we can buy today, they do work in the matrix plane. So all the relations are mapped. So you see here, for instance, if you look, do you see my, no. Anyway, if you look on the matrix on the left, you see that component 3 as a relation depends on component 2 and component 7. This is what it means. Dsm Analytics will try to permute the matrix until it finds a diagonalization of the matrix. If there are still elements below the diagonal, it means that those components are involved in loops. And loops are not good. Why they are not good? Let's imagine you're responsible for function 1. And function 2 depends on function 1. If you make a modification on function 1, it will affect function 2. Probably the function owner for function 2 will have to rework function 2. If function 1 also directly or indirectly depends on function 2, you fall in a loop. So it means that what you've changed on function 1 will affect your own function, and probably usually in a negative way. So you want to avoid those loops. They are no good. So DSM Analytics help you find those loops. Also, DSM Analytics can help you find cluster in your system by block diagonalizing your matrix. Each block is a cluster if the blocks don't have any overlap. So it means that those clusters are independent from each other. And it's super interesting for a project owner to know that, because then we can plan the project teams in a better way. We know that, okay, those people can work independently from us. We won't affect them. A byproduct, very interesting byproduct of the diagonalization of the matrix, so the second use case in the middle, is that we also get a sequencing, the best sequencing order in which you have to specify or develop your functionalities to optimize the development time. So it's really cool features. When we looked into that, we realized quite quickly that every single algorithm in DSM Analytics are coming from graph theory. Functional disposition is mapped in a graph. So why not apply DSM Analytics to the graph directly? So let's forget about matrices. In the graph, it looks like that. A loop is a loop in a graph. It's direct. One can see it. One can query for them. A cluster is a cluster also, so it's quite simple to see. Anyway, sometimes looking at it in the form of a matrix anyway help the system engineers understand. So we have created a little app which is not yet integrated in this application that we are developing now. It will come next. That does just that, DSM Analytics in the graph plane. So let's have a look here. Let's look at functional disposition. Check how it looks like. A big mess. And let's try to triangularize that. Now, we didn't really optimize it. We do it with Cypher directly. We could have probably make it better by using the traversal API for Neo4j. Probably we could get this result in a millisecond. But 10 seconds or so is enough for us because we don't triangularize this matrix that often, basically. And so here, let's have a look at the result here. Here we see, okay, we didn't manage to triangularize the matrix. There are still a lot of components below the diagonal. So it means there are still a lot of components, all of those, involved in loops. So it's very interesting information. Now, system engineers, function owner, can work together and try to reshape a little bit the system. Maybe this functionality shouldn't do that. Maybe it should do it that way instead. Let's try to make a product design without loops. So that's what people have been working on. So I've loaded actually the solution into the system. And so we can look at the result after getting this information from this application and working on it. So we'll run the triangularization again. Okay. It's quite fast anyway. And after reworking, hopefully, yes, it's triangularized. So it means that the system today is much better than how it was before. Because virtually, yes, there might be a few mistakes here, but virtually, the number of loops in the systems has decreased by 1,000 or something like that. So we improve quality a lot. We can also use the Dsm Analytics to find if there are natural clusters inside the system. So let's clusterize all that. And we see that maybe there are 2, nearly 3. But they are not completely decoupled. You don't see what I'm showing on the screen, sorry. But they are not completely, you see. All right. So they are not completely decoupled. They are still an interface. In the graph, you see it through this node here. Right? This is the interface between 2 nearly decoupled clusters. Maybe we can do even better then, not searching for natural clusters, but we can force clusters into the system design. Why do we want to do that? When we develop a new car, we will want to test it. And maybe first we just want to test it on a test track. That's enough. So to test a car on a test track, it's enough to be able to unlock it so I can get in, accelerate, brake, turn, stop the engine. Maybe that's enough. Get the speed information. So a subset of functionalities is enough. Then we will want to test the new car on the road. And here we have legal requirements. So we need to put more functionalities to fulfill those legal requirements for testing on the road. And then maybe we want to add a third cluster of functionalities for improving the vehicle dynamics, for instance, or getting some comfort functionalities. So that's what the engineers have done. Where is it? Neo4j here. So let's have a look. They have created those yellow nodes here, which actually, which are cluster nodes. And they've related those functionalities to those cluster nodes. So that's interesting. We see that basic central locking again, and vehicle locking and unlocking, both of them are involved in the 2 clusters. So it could be interesting to split those functionalities, because some of it has to be done for the first cluster, the rest can be done later. So we also have a little split functionality in this application that will do just that. So it's all splitted. And we can look at the result of it. Let's see here. So now it looks like that. So we still have our 2 clusters, but now we see that vehicle locking and unlocking and basic central locking are splitted in 2. And there is this split relation in between to keep the information that actually they are 1. So this is our interface. This interface, we'll have to solve it anyway at some point, but maybe not now. Now we focus on delivering a car we can test on a test track, let's say. And so if we go back to our little application here, trying to clusterize it again, see the result of this splitting, what has happened. So here in the graph, you see it directly. We have our nice clusters. We can work on them. And obviously, in the matrix, it appears like that also, blocks on the diagonal. Now, let me go back to the presentation. For project planning, so I talked already a little bit about that. By triangularizing the matrix, getting rid of all the loops, we get also the best sequence in which we can work on those functionality to optimize the work. So with the clusters and this sequence, we can let the project leader plan their project in Jira, which is the project planning tool we are using today. And so they know, okay, we'll focus on this cluster of functionalities, and we have to do this one first, this one second, this one, maybe we can, those 2 are not dependent of each other, we can do them together, etc. So it helps to plan the project. And this is something we've started integrating into our Graph Intelligence platform in a little app, which is under construction now, but which is basically showing how those functionality relate to each other, when should we develop them, in which PI, program increment, which is period of 12 weeks at Volvo Cars, and which team should do it. So the loop is closed, nearly, let's say. Yeah, that was it. Thank you.